Hello, everyone. My name is Danny Chung, and the paper I want to introduce today is Larger Scale and Fine-Grained Vision, Language for Training for Enhanced City Image Understanding. So this is my outline. I will first introduce the topic of this paper, and next we will look at the details of the methods proposed in this paper, and last we will look at the experiment result. Okay, so let's get started. So this paper proposes a fine-grained vision language model that trains an artificial intelligent agent to interpret CT scans by aligning anatomical regions with their diagnostic descriptions. So this topic is important because high clinical burden. So radiologists face overwhelming workloads analyzing hundreds of 3D slices across multiple anatomies. And it's important also because of the supervised artificial intelligence bottleneck. So what bottleneck? So currently, the supervised model will take into a image input and will output the classification result, but that is not useful in the practical world because we need precise disease tables to train the model, but it is hard to cover the complex condition in the real world by only these labels, and also to annotate the data, to label the data, it will add extra load to the radiologists. On the other hand, for a visual language model, the output is a textual output, which is similar to the diagnostic report. So we can directly use the existing diagnostic report to train the model. So the current gaps in the visual language model is that they align the entire image with entire reports and miss the anatomy level details. So the consequence of doing this is that the model may wrongly associate irrelevant regions with diagnostic text. So for example, here is the attention map for a previous model called CLIP. And as you can see, the model highlighted very large region in the image. However, most of these parts are not relevant to the disease indicated in the report. And on the other hand, you can see that their proposed new method only highlights this part, which is indicated in this report. So the main contribution of this paper is that they perform anatomy level decomposition and matching between CT images and report text instead of using global alignment. And also they introduce some methods to reduce the false negative rates. And lastly, they created a large CT dataset to help the training task. And here is the quantitative comparison of AUC scores across 45 disease diagnosis tests in 15 anatomies. And you can see that their model performance is a lot better than the CLIP model. Okay, so let's look at the details of the methods. The first part is the data processing. So there are two methods in data processing. And first is anatomy parsing. So there are two steps in this method. So first, we will segment CT scans into 104 anatomical regions using this tool, Total Segmentator. And we will group these 104 regions into 36 major anatomies to match a typical style in the radiology report. So why we do this grouping? So for example, for lung, this total segmentator will divide it into 5 regions. However, in the radiology report, doctors usually just say that the lung inflammation without mentioning which specific regions. So this grouping will help avoid problems for from incomplete or ambiguous localization in reports. In other words, this grouping will help maintain balance between details and consistency. So next is the report decomposition. So the original reports look like this, and the first step of the decomposition is that they will use a language model and string matching to find all anatomies mentioned in the report, so such as liver, kidneys, stomach, and so on. And the next step is that they extract the anatomy-specific text description. So as you can see, the content relevant to the liver is highlighted in blue, and content relevant to kidneys is highlighted in purple, and so on. And the last step is to combine the text together to form the anatomy level decomposed report. So you can see that the liver for the findings and impression is combined together to one report, and for the kidney is combined together again, and so on. Okay, and this anatomy level decomposed report will be fed into textual encoder next. Okay, so let's look at the next part, the fine-grained constructive pre-training model. Okay, there are many components in this pre-training model, so let's look at the visual encoding first. So we'll pass the CT volumes through the image encoder and to get a 3D grid of visual tokens. And next, we will apply the segmentation max to select only the relevant visual tokens. And next, we will add the learnable query tokens for each anatomy and update it using the self-attention with selected visual tokens. And lastly, we will project and normalize the updated query token to form the final anatomy-specific visual features. Okay, next is the textual encoding. So we fed the previous anatomies level decomposed report into the text encoder, and they use BERT in their paper, and we project and normalize the tokens to get a textual embedding for each anatomy J of patient I. And with the textual embedding and the visual embedding, we compute the similarity between them across all patients in the batch, and we will the similarity can be calculated in this formula, and we will normalize the similarities using softmax. And next, we will use the constructive loss to pull matching anatomy pairs closer and push apart non-matching pairs. Okay, and the next part is to the methods to reduce false negative rate. So the previous fine-grained framework will increase false negative rate in contrast learning because of two major reasons. The first is that by doing the report decomposed, we get more normal anatomies in the data, but these normal cases of each anatomy will have considerable variability in the descriptions, and all of them will be wrongly pushed apart during contrast learning. So it will be important to identify the cope with these massive normal samples. The second problem is that the similar diseases in different patients will be treated as negative. That is to say, the different image report pairs with the same anatomical disease may be wrongly treated as unrelated, but it should not be like this. So the solution of the paper for the first problem is to use the dual false negative reduction. So the anatomies not mentioned in the impression section are considered normal. And for anatomy J, if both samples are normal, they will set their label as a positive pair. And lastly, they will normalize corrected labels so that the summation of all similarities will equals 1, and to ensure the stable learning. And for the second problem, they propose a bootstrapping strategy. So this strategy will utilize the similarity scores predicted by the model itself to correct the target label during contrastive pre-training. But this strategy have a side effect because we use the similarity scores predicted by the model itself. This will introduce bias into the estimation, and this will degrade the model performance. So the paper proposed another method to help this strategy. So this method is called teaching training framework. So we will train two models that help correct each other, and one model's prediction are used to adjust the training targets of the other, like this formula, and this alpha is a tunable hyperparameter. Okay, so that's the details of the methods in this paper. Let's look at the experiment result. So for the training dataset, they use their self-created dataset and also a CT rate dataset. And for the test, they use the red chest CT. And the evaluation metric is listed at here. So the first experiment is the zero-shot abnormality detection. And as you can see, their models outperform all other models. And especially you can see that they suppress the clip at about 13 points on AUC and 10 points at ACC. Compare with the second best model, it has 10 points higher than in AUC and maybe 7 points in ACC. And the next experiment is to compare with the current state-of-the-art method. And you can see that their methods have a significant improvements. And the next test is the radiology report generation. So they let the model to generate full diagnostic reports from the CT images and see which model have which result of the model is closest to the radiologist. And you can see that their model have a very good performance. And the last experiment is the ablation study. So they test these components and to check if these components contribute to the improvement of the performance of the model. And you can see that all proposed components contribute to the progress of the performance. So that is for the experiment result. So the remaining gap of their method is that also it is powerful, but it still needs streamlined processing and better alignment between model design and report generation tasks. So that is my report. Thank you.